Okay. So we want to get onto speed with batch RL. Everyone heard about batch RL? No? What is batch RL? Fake RL. Okay, Shimon says fake RL. Why is it fake?
Because isn't RL supposed to be about interaction? Like batch RL is good, but why is it RL?
Yeah, no interaction. Right. Well, is RL about interaction? It's reasoning about interactions, right? So it's like the causal part of it, right? It's like you're still reasoning about interactions. So what is this batch RL? The batch RL is that you have just data, right? And from that, you want to get policies for some imagined MDP that supposedly somehow generated the data, and then you want to deploy the policy, but the loop is never closed, right? So it's like, no more data generation after that. So it's like, maybe you could call it not fake RL, it's broken RL.
Isn't it just
like
RL for prediction?
Huh?
Isn't it just RL for prediction? Like we only care about the prediction part. That's it.
Yeah, if you generalize the idea of prediction to predicting what works, what doesn't work, maybe it's just decision making, like good old-fashioned decision theory, like what decision should I make based on a batch of data that I collected in some way.
Oh wait, are we assuming that we collected the data, or is that an assumption we're going to be making?
Does it matter who collects the data?
Oh, I just thought that like if we say that we collected the data, then we have access to the policy that generated the data.
Oh, that's a sub problem. So who collected the data? Well, maybe they know about how. Maybe the question is, how was the data collected, right? How was it collected? Do we know that? Does it matter? Right? So maybe yes, maybe no. These are different branches. Maybe we can control how the data is collected. So maybe we are in this pre-experimentation phase. We can think a little bit about, okay, how should we collect the data as well. I categorize all of these questions as questions surrounding these bigger batch RL things. So more systematically, like it starts with, if you were a statistician, you would say it's experimental design, right? How to collect the data. All right, and if you have the luxury to decide about this, that's great. Sometimes you do. Very often there are like big restrictions on this. Otherwise, you would close the loop. Otherwise, you would just run this loop, and then you wouldn't need to deal with fake RL. You would be running in a loop. And so usually in this batch RL, like people argue that this is a practical constraint that practicalities, due to practicalities of the problems that we face, you can't really go in and then say that, oh, let's deploy this policy, and with this policy, let's collect more data. Because people are too scared of that. But then you might be wondering about, like, are you ever going to give me the license to deploy my policy ever? If you're too scared of this, what do I need to do to convince you that you should deploy my policy? So there are questions surrounding, like, that's the beginning, like experimental design, and then there are lots of algorithmic questions, and then the end of it is going to be certification, right? Can we certify the performance of the policy to put the person at ease who is responsible for running the whole thing, that it's okay to deploy the policy? And then, yeah, like, there could be good reasons not to close the loop. Even in this case, you might be thinking that, oh, that's almost closing the loop. Well, no, that you deploy your policy, you can collect some more data, but that's not quite the same as just, designing an experiment to learn everything about the system. Then you would run a wide experiment, like trying many different things. And when you focus on certifying for performance, then maybe you don't deviate from the policy that was initially deployed or whatnot. There are all kinds of considerations. And so you're going to stay close to the data distribution that was originally used, and therefore that's not the same as closing the loop. There is something in between, which I like to think about as conservative exploration or something like that. But that's halfway in between. So I just to say that, like, yeah, there are things in between. For example, maybe your boss wants, like, no more performance drop at any point in time than 10 performance compared to the baseline. And then somehow you can guarantee this, and then you can still explore. Then you can close the loop. Everyone's kind of happy. That's halfway in between full-blown crazy exploration where anything can go, no one's going to be hurt. If you do something bad, the boss doesn't care about it that much. But that's not better. So that's more already on the online side, because then you're wondering about, okay, what to do in the loop. Although there is restriction on what you can do in the loop, but there is a loop. So if you're not closing the loop, then that's like the classic case of batch RL. And the reason you would have something like this is just these practical reasons. Like, someone collected data is sitting on a desk. Why not try to use it to come up with something better? Okay, I see that Roshan's asking some question. Could another way to think of these settings be that there is a human in the loop between the algorithm and implementing the policy? So you want to control the number of policy changes, so the human doesn't have to do too much work. Yeah, you can think about this. Yeah, so a few certified changes where the human has some oversight, and then you can't do too many of these updates. Anyways, all right, so besides how to collect data, there are questions like, okay, how to use the data. So that's called policy optimization. And people like to put an O everywhere. So it's OPO, of policy optimization, because maybe, you know, the data was generated with following some policy, and then you are optimizing policy and the distribution induced by this policy. It's off the distribution. Now, your new policy is going to be off the distribution of the old policy, and that's important for algorithm design. So they call this whole thing OPO, of policy optimization. So that's kind of the ultimate goal. An intermediate goal, which is related to this final end product, is of policy estimation, OPE, which is the subtask of trying to predict how well a policy is going to do in some circumstance, let's say some issue distribution, and maybe get a certificate as well, like with high probability, the value is granted to be above some bound, if you can do that. So see, these are the subtasks. Okay. So in the theoretical analysis of all of this, of course, we're interested in what are the limits of this and how to approach the limits. So what are the best ways of doing things? And I want to start with the simplest idea of all, because it also connects very nicely what we have been talking about in the past, which is this idea of getting your data. So here's your data. It sits on this old-fashioned disk. So that's your data. And then build an MDP model. And then get a policy for that model. And okay, so there was this MDP that was generating the data somehow. And then deploy the policy on the MDP that was generating the data, and look at how well it does. So this is model-based, I don't know, like policy optimization, if you want. So this step is the step which we call planning, right? So how to extract a policy from a model, which is good for that model. And we were focusing on the case when we take it for granted that the model that we are working with is the same as the model, that the policy is going to be deployed. We never talked about what happens if that is not the case. Should we be doing something differently or not? And so today, that's the first question that we should look at. Do we need to worry about the errors induced due to the estimated model being different from the true model? How do modeling errors propagate into the suboptimality of the policy when it is deployed in the original MDP, right? So that's a very basic question. And we're going to have some clean answers to that question. So model sensitivity. So again, we have this MDP M hat, which has a state space, action space, has a transition probability, and the reward function, maybe we are in the discounted setting, so the discount factor is going to be the same between this model and the true model. There is also the true model. And at the beginning, let's not just worry about how we're estimating the transition kernel and the rewards. Take a high-level view. Like whatever way you do it, it's okay. Like the error analysis is going to be independent of that. And also, let's not worry about the details of planning, because you can do planning in so many different ways. Like after all, we spent half a semester on just talking about planning. So let's get a policy, which is a policy which is, well, it's gonna be, you know, assigns probabilities to actions given states. It's a policy for both M hat and M, so that's good. Like both MDPs share the same state action space. That's kind of like a basic requirement here. So once we have this policy, so we arrived at this policy using a planner that works on M hat. The guarantees that we usually get are of the form that if you look at the value function of the policy in the MDP where planning was happening, I call all these quantities which are with respect to this approximate model M hat, like I denote them to putting a hat on the top of everything. So the value functions are going to be V hat, action value functions are going to be Q hat, and so on and so forth. For the policy, I don't put a hat because like it's a policy in both MDPs. There's no need for a hat there. So the guarantee that we have is that its value function is not far off from the optimal value function of this MDP. So if the planner is doing its job, then like with a small epsilon, this is what we get. And the question to ask is whether from this, it's going to follow that if you deploy this policy in the MDP, so that's just like the standard value function in M now, then the value of this policy in M is going to be, you know, not bad. And delta is I don't know, shouldn't be too big compared to the epsilon. So I don't know, like it's epsilon and like some function of epsilon and all the other usual culprits, right? Oh, and maybe somehow we should account for the differences between M and M hat. So somehow M and M hat go in, and the question is like, what should be this F? So what an F can we use there? So can we bound the suboptimality of the policy when it's deployed in the original MDP if it was planned for this approximate MDP? All right. I know we should recall our results for where is it? Policy error bounds. Maybe it's in this approximate policy iteration. No, it's gonna be maybe here or in the next one. I think it's maybe the next one. Yeah, there is this theorem here, or lemma, the policy error bound. So we want to rely on this. It starts by saying if the policy was epsilon optimizing in the sense that, you know, like you apply this M pi operator to Q star, then you get almost V star, then it follows that the policy cannot be bad. So there's a blow up by a factor of 1/1 minus gamma, but that's it. Like that's part one. And part two of this result says that if pi is greedy with respect to Q, then pi is 2 epsilon optimizing with this thing. So we want to start from this result. I just want to look into my notes so I don't get lost. All right. So policy error bound. Says if MP Q star is greater than equal to V star minus epsilon times this all one function, then the policy is at most epsilon over 1 minus gamma suboptimal. So that was part one. And part two was that if a policy is greedy with respect to some action value function, it doesn't matter what action value function we are getting it from, then it follows that the policy is 2 times the difference between Q and Q star over 1 minus gamma suboptimal at most. So now what we can cook with is this inequality. So you don't want to rely on how policy, how we got a policy. So from this inequality, we can derive something for some action value function. So you want we want to use this thing. And so the question is, what should be this action value function that the policy is greedy with respect to? Well, we don't quite know, but we can get something close to this. So if we choose as Q, we're going to choose Q hat of pi, then what can we get? So, of course, Q hat of pi is not larger than Q star, right? And so from this, it follows that MQ hat of pi is not larger than M of Q star, Q hat star, sorry. So that's like V hat star. Okay, good. And so if you want to reason about M of pi, Q hat of pi, clearly M of pi, Q hat of pi is even smaller because M is like this maximum operator, right? So it's maximizing with respect to the actions, and M pi is just choosing some actions. Wait. Yeah, so M pi, okay, we are not going to need this. So this is equal to V hat of pi, right? So that's just the connection between the action value functions and the value functions. And by assumption, so by star, this is smaller than or equal to v hat of star minus epsilon times 1. Oh, okay. And this is equal to m of q hat star minus epsilon times 1 by the definition of v hat star and mq hat star. And then using this inequality, we get that this is greater than or equal to m of q hat of pi minus epsilon times 1. Right, and also it's very clear that you can just replace m pi with m and you get something smaller, something bigger, because m is this maximum operator, right? So m pi selects a certain action according to policy pi, and m just says that select the best action that maximizes the action values in all states. So that must be better. So from this, it follows that, well, m pi q hat pi is not quite equal to, so we wanted something like this, but so we get that, okay, like it's a sandwich between m of q hat of pi minus epsilon and m of q hat of pi. So you can write m of pi q hat of pi as m of q hat of pi plus some z, where this z is a function whose max norm is bounded by 1, right? So just the error term cannot be big because of this sandwiching. Okay. So now we have to think back. We can't really use 2, but we can think back of how 2 was used to derive the error bound that is seen here. Who remembers how that error bound was derived? It's in front of you.
Replacing q hat of pi with q star minus epsilon.
Yeah, basically we want to show that we can use the first part of this lemma, right? So we want to relate q and q star, and from that we want to show that m pi, sorry, if q and q star are close to each other, then it's going to follow that policy pi is almost optimizing, right? Like up to the degree to which degree q and q star are close to each other, because policy pi was greedy with respect to q. So if q is very close to q star, then of course it should be almost optimizing q star. Okay, so we're going to repeat this derivation. Let's do this. Well, actually, let's just do it more generally. So let pi be a policy such that m pi q is equal to mq plus z. Then we want to show that m pi of q star is big, so that we can use this case. So this is, of course, the same as m pi of q plus m pi q star minus q. M pi is just linear. And m pi q is equal to m pi q, mq plus z. So this is equal to mq plus m pi q star minus q plus z. Okay, so that just by this identity. And now we want to bring back q star. So this is equal to m q star plus mq minus m q star plus m pi q star minus q plus z. All right. And so we need to lower bound this by some constant times the all ones function. So this guy can be lower bounded by the difference between these two in infinity norms times 1. And actually, it can be further. I mean, okay, so let's do it this way. This is too messy. So mq minus mq star in infinity norm is upper bounded by just q minus q star in infinity norm. Therefore, mq minus mq star is lower bounded by the negative of q minus q star in infinity norm times 1. And similarly, m pi q star minus q in infinity norm is upper bounded by q minus q star. So therefore, m pi q star minus q is lower bounded by the negative of q minus q star in infinity norm times 1. And of course, z can be lower bounded by the negative of its infinity norm times 1. So altogether, what this gives is that m pi of q is lower bounded by m q minus 2 times q minus q star deviation in max norm plus the deviation of z, or like the max norm of z times 1. So that's our epsilon that we can use. And by this policy error bond, so that's this epsilon that we can use by the policy error bond by this part 1. The policy error is epsilon over 1 minus gamma at most. So from this, it follows that v pi is at least v star minus 2 times q minus q star plus, so the deviation like between q and q star and the deviation of z divided by 1 minus gamma times 1. Right, so that's the generalization, a slight relaxation of this second result where we allow this second result where we allow some errors. Right? So you can use this with q hat of pi. So now back to our calculation. We see that, well, we can use this with q being q hat of pi. And so it follows that v of pi is at least as large as v star minus 2 times q hat of pi minus Q star infinity norm plus Z infinity norm 1 minus gamma times 1. Wait, what was this Z? Oh yeah, like that was our original epsilon. So okay, there are no other epsilons. So that's our epsilon. Right? Remember that we said that we know star, right? Like this thing in blue, that this is the epsilon. We know that policy pi is epsilon optimal in this approximate MDP. Okay. So let's just upper bound this. So let's do the rest of the calculation, not writing anything else, just this. And actually, we're not going to change the epsilon part. We're not going to change the 2. So just upper bound Q head of pi minus Q star. In terms of quantities that are more relatable, right? Like it's Q head of pi, like what is this? Like we still don't quite know what that is. And the obvious way to do this is to use a triangle inequality, because we know that policy pi is almost optimal in M hat, in this approximate MDP. So we're going to relate this to Q head of star, sorry. And then we're going to relate Q head of star to Q star. So how about the first term? Well, the first term is bounded by epsilon, right? Because we know that the value functions are disclosed, and the action value function is just like adding reward plus gamma times transition times value function. So they're also disclosed. Actually, you can even add the gamma factor because transition probably is bringing a gamma. So maybe I add the little gamma to remind us what this calculation was. And for this guy, there are 2 ways of bounding it. And both of them rely on like the classic thing that we always do, which is that if you have a contraction, a gamma contraction over some norm space, and its fixed point is x, then for every y in the domain, the y is cannot deviate more from x than how much the operator deviates on y divided by 1 minus gamma. So if, like you look at a y and you say, oh, it's almost fixed point by applying the operator to it once, and then you almost get back the original thing, then that means that yeah, indeed, it is almost a fixed point, right? So how do we get this little proposition? This is, I think that we did this many times. So you can just like introduce this T everywhere. And use a triangle inequality. And then use that T is a contraction. And then move this to the other part and then divide by 1 minus gamma. And you got the inequality, right? Just reorder and solve for x minus 1. Use this like a zillion times, different ways. And now back to your question of like, how do we bound this? So this deviation of q hat star minus q star. And we can go both ways, like two ways. We can take the Bellman optimality operator for m hat and use that. And use that q hat star is the fixed point of that. That's like saying that x in the above lemma should be q hat of star. Then t has to be t hat. And so the above lemma just says that this is the same as t hat applied to q star minus q star. So we have to check how close q hat star is to be a fixed point of the Bellman optimality operator of the approximate MDP. And of course, q star is a fixed point of t, where t is the Bellman optimality operator. Now here it was a general guy. Here it's very specific. It's the Bellman optimality operator. So t hat of q star minus q star is equal to t hat of q star minus tq star, because q star is a fixed point of t, and t hat is equal to okay, t hat applied to q. Just recall that this is how it looks like, and this is how t looks like. It's the same m, just the data is different. Sorry, it's a hat here, and there's no hat here. So they look like the same, except that the r is swapped to r hat and p is swapped to p hat. So if we swap this in, we use that m is a non-expansion, then we get that this is upper bounded by r hat plus gamma p hat q star minus r plus gamma p q star, which is upper bounded by triangle inequality again. The difference in terms of the rewards in subnorm plus gamma times the difference between the transition operators applied to q star in infinity norm. Okay. In an entirely symmetric fashion, you can also get that t. All right, so here we started with that q hat star minus q star is upper bounded by like plugging this t hat there, and then q star remains. So the symmetric way of doing that thing is just to say that q hat star minus q star is upper bounded by tq hat star minus q hat star in norm divided by 1 minus gamma, and then the difference in the numerator can be upper bounded. Similarly to what we have seen, the only difference is going to be that here we have q hat star. Oh, and if you want, you can upper bound this further by the induced operator norm difference of p hat minus p, and times the magnitude of q star. If you want, you can upper bound this by 1 over 1 minus gamma, but I kind of like to keep this around, but just keep in mind that you could also do this. I like to keep them around because they're helpful. And this further upper bounding can be very, very conservative. So for one thing, maybe the range of Q star is much smaller than the full possible range, 1 over minus gamma. The second thing is that maybe P hat is not really a good fit everywhere to P, the transition cutoff, but it is good fit, so to say, in the direction, like in the way it acts on Q star, it might be a good fit. And if that is the case, then like that's sufficient to get a small error, and that's important. And maybe it's even more important to when it comes to this guy here, because here Q head of star is somehow under our control. We have the approximate MDP in our hands, and like maybe we can measure this error and try to estimate it. Maybe we can try to reduce this error, and that is going to lead to some procedure that later we're going to talk about that can be used to fit MDPs, right? So if you want to fit an MDP to some data, how do you want to do it? You should try to do it in such a way that the error at the end for the policy that you read out for the fitted MDP, when it's deployed in the original MDP, is not large. And so maybe the best thing is to start with an error bound and look very carefully at the terms. And here maybe stop early in deriving these error bounds where you can measure the quantities of interest and you can derive an upper bound on the error, and you should optimize the upper bound on the error, right? So that's an idea of how to fit models, which we will see later on. Anyways, if we put everything together, what do we have? Well, it got a little bit long, right? So it's so long. Let's call it a theorem. I don't know. It's just a lot of triangle inequalities. So let pi be a policy such that in this approximate MDP, its optimal value function is, its value function is epsilon close to the optima. So it's an epsilon optimal policy of the approximate MDP. Then it follows that this policy is going to be delta optimal with delta not larger than, and then we have to think back. Okay, like let's collect the terms. So we have 2 times, okay, can you guys, I can, look at this, copy, paste, there you go. Well, there is this epsilon over 1 minus gamma, so let's write it down. That's clean. And then there is this factor of 2. Okay, let's write it down. And then there is, okay, not factor of 2, but 2 over 1 minus gamma. And then we need to get the upper bounds on this guy. And that's going to be a longer story. So we're going to have another 1 over 1 minus gamma. Okay, like this. If we were in a classroom, this would be so much easier. So, and then we need to get the bound on this guy. What is that? That's going to be here. Haha. And we could bound this term in two possible ways. When we bound it in the other way, we got almost the same expression. We can take the minimum of the two. So just a side note, mean a minimum between two numbers. I like to denote it with this binary operator because it's just so much more handy than writing min. All right. Cool. These guys can be gone. All right, so this is the theorem. Closing one parenthesis. And if you wish, then you can upper bound it. So that is, the epsilon has some price, but it's probably not too big. And these other guys, if you want, you can upper bound further these things. And then if you upper bound, the Q star is upper bounded by 1 over 1 minus gamma Q hat star, similarly upper bounded, they become the same. So then you see that if you measure the errors in this infinity norm, then this is how the error looks like. Right? So what's the lesson? Well, if you just look at the very end, you see that if you're controlling the error of approximating rewards, the error of approximating transition probabilities in these appropriate norms, and you're controlling your optimization error, then you're controlling the suboptimality of the policy. There is stability, right? Like small errors induce small modeling errors, induce small errors in the policy side, except that maybe we should be worried about that. These errors are blown up by a factor of 1 over 1 minus gamma squared. That could be pretty large. So for large horizon problems, maybe this is this could be worrisome. Like you need to make these errors very, very small compared to the horizon. I mean, like reasonably small compared to the horizon. And we also see that the error on the transition cutoff should be made even smaller if we are in the bad case that Q star or Q hat star, they have large magnitudes. If they don't, then it's okay. Like if, you know, like the sum of the rewards along any trajectory is at most 1, it's like, you know, you either win or lose, that sort of thing. It's quite common. Then you don't have to worry about this that much. That's a nicer case for modeling errors. Okay. Any questions for this? Well, the results that you standardly see in the textbooks are just for epsilon equals 0, but this is not much harder to get, so why not? All our policies for epsilon approximate anyway, so it's good to have this slightly more general result. Okay, there was a question whether we're missing something. Oh, yeah. It's a good point. I think we are. Yes. There was a triangle inequality. A gamma times epsilon. Ha, 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 ha. All right, that's this guy here. Thank you. So where does this go? It goes together with the epsilon. All right. So the epsilon, instead of an epsilon, we should have epsilon times 1 plus gamma. Yeah. Good job, lad. Thank you. So Shivan was asking whether the definition of t hat is correct. What do you mean? Oh, no, no, no. Yeah, right. Like none of that is correct. Oh, look at that. That's for value functions. If you have action value functions, then it's the other way around. How could I mess this up? The end result is the same exactly. Right? Okay. Good, good. All right. So this is some basic reassurance that things cannot go awfully wrong, perhaps. And it also gives us some clue to what to watch out for when you're doing model fitting. You should fit the rewards, you should fit the transitions. When fitting the transitions, does it matter that you're fitting the transitions like to mesh the errors everywhere? No, it doesn't matter. It's more like the directionality of this next state distribution only with respect to Q star matters, right? Like it doesn't matter otherwise. What is this? Like this should be V star. It's the same, okay, like trickery, right? Okay, let's fix these things. Oh, look at that. That's ugly. So that should be a V star there. Right. Just going to make everything red here. This makes more sense. Like P and P hat cannot be applied to Q star. They're applied to V star. Where did I put my brain? Okay. All right. Ha! Cleaning it up. Hey. Good. This makes more sense. So it's in the direction of V star and the direction of V hat star. Either of those directions, here you have a match, you're good. Right. Back to batch array.
There are some questions.
Oh, there are some questions. Good. Rewards in 0, 1. Well, okay, so for the very last one, rewards in 0, 1, nothing else used that rewards are in 0, 1. This gamma shouldn't go anywhere. It can go away, but like you're just making things looser. Good points, man. All right. So let's go back to batch RL. So I guess first we should see whether we can do batch RL in this small MVP case, right? Like the way we started with planning as well. Like let's clean up things for where you have finite state action spaces and see what we can get there. And then try to generalize it to the cases when you have features or whatnot. So tabular. And then we're going to do the featurized case later. So for the tabular case, for both of the cases, by the way, so you can also ask the question of how is the data collected? And here, two basic strategies are trajectories or it could be that, so in the case of trajectories, maybe you have a bunch of initial states or just one initial state, and then you will be interested in finding a policy which works well from that initial state. Okay, let's keep that thing simple. Or the other case could be that you control which state action pairs get sampled. It's like you have an offline access to a simulator. I mean, like, okay, so you can tell the simulator how many times you want which state action pair before actually seeing the data. It's like kind of weird, but so you're going to control how many observations you get for each state action pair. It's a little bit artificial, but why not? Like, there are these two cases. So when we're talking about trajectories, we're talking about trajectories of some policy. And this kind of standard terminology for the policy that generates the data is to call it the behavior policy. But it's also called the logging policy, which in a way makes more sense. The behavior policy is like, it's some terminology that is used when somehow like batch RL also comes up when you're running online RL and you're running your policy in an online loop, and then you're collecting data, and then you're going to use that data, you collect a batch of it, and then you're going to use it for coming up with some other policy. Then people talk about that, oh, I had this behavior policy that was generating the data. So that's also another place where somehow batch area can be a subroutine in online area, right? Like it's simple. And this terminology comes from that literature. Anyway, so you have this behavior policy, and then let's most of the time we assume that it's a memorized policy. That's a simple case. So let's look at the tabular case, and then, well, when it comes to model building, does it really matter how the trajectories, how the data is generated? Whether it's like for every state action pair, you get a bunch of observations, and whether it was trajectories or not. When it comes to estimating the model, how would you estimate a model? Like you collected data in this way or that way. Like you have basically like these little snippets of like state action, next state, reward, where the next state is from the transition kernel of the underlying MDP, and the reward is from the distribution that generates the reward. Like we're going to assume that the rewards could be random too. Because of the Markov property, it doesn't quite make any difference. So you can just estimate the model the same way. So you can in fact just think about that you have at time t, you have a state S, T, and then action A, T, and then you get to see a next state and the reward. And this next state is from the distribution from the transition kernel of the MDP, and the reward is the, I don't know, we didn't use any letter for this. I don't know, I just put a tilde on the top for the lack of a better idea. So here, this is distribution over the reals, and here this is distribution over states. So dots, dot means state or real number set of real numbers, set of states. And so this is the data. And to estimate a model, like a simple idea is to say that, well, I need reward estimates. So let's count. Okay, so T is going to go from, I don't know, 1 to N. So that's the total amount of little snippets, whether they are from trajectories or because we systematically chose each state action pair a bunch of times. It's the same. And you can count how many times a given state action pair appeared in the data. Oh, let's call that with a capital letter because I like to stick to using capital letters for random variables. And that could be random. So so this just counts how many times we have seen the given state action pair in the data. And oh, if we are dividing by 0, that's going to be a bummer. So let the reward be 0 if NSA is 0 because of lack of better idea. And other than that, we can just filter the data and then just pick out the rewards that correspond to time indices where we have seen this specific state action pair. So that's estimating rewards, and you can estimate transition probabilities in a very similar way, right? So you could say that, okay, let's just that be. The same thing, except that here the data is in a way whether the next state is S prime. All right, so it's like, okay, that can't be 0. It's like let it be P naught of S prime, where P naught is just, okay, let it be the uniform distribution. So we don't have any better idea. So otherwise. Right, so when we are collecting trajectories, like data with trajectories, then this NSA is random, it's a little bit uncontrolled. In the second case, the NSA is just like these preset numbers, and they're controlled. And so we saw that we need to know how well we're estimating the rewards and how well we're estimating the transitions. And for both of them, you can just use Hovding's inequality to get some basic bounds, right? So so let's say that we're in this case much simpler than the other because we don't have to handle the case when the number of observations is 0. Just like annoying thing, it's nothing really too complicated. Just don't want to write that. Then Hovding's inequality. Okay, so this is going to assume that all the random rewards are also in the 0-1 interval, just for the sake of simplicity. Then Hovding's inequality gives us that this is smaller than log 1 over delta divided by 2 NSA. Right. And you can get the same thing for PA SS prime minus PA hat SS prime minus PA SS prime. And you get the same thing. If you want, like, since we need to control the error for every state action pair, we need a union bound. So these hold individually. If you need to make them hold uniformly over all the states and actions, you can divide data by SA. And then these bonds are going to hold uniformly. So then what holds is that with probability 1 minus delta. Okay, so here you would need a unit bound, over state action pairs and next states. So then this holds for every state, action, and next state. And if you recall P hat minus P infinity norm, so that's this mixed norm where you take the maximum over the state action pairs, and then you take the L1 norm difference between the next state distributions. And so this is going to be upper bounded by, so this is the sum of these deviations over S prime. There is S of them. So you would get this S times square root log S squared A divided by delta over 2N, NSA. And that's all right. And you also get that R minus R hat in the infinity norm is smaller than this log. I guess you have S squared everywhere. It doesn't matter, it's inside the log. Right, so you can get this. And then you can solve the MDP. And look at the error bound. So maybe your epsilon is 0. And you see that like, oh, I need to control this R minus R hat and P minus P hat. And the smallest count is what's going to matter in my upper bound, right? Like if I have one state action pair, which was in the data set very, very few times, then that would just like make my upper bound large, right? So the error that you get at the end, so the delta that we had was, okay, let's ignore the epsilon. Epsilon is 0. There was a 2. Where 1 minus gamma squared. And then there was 1 square root. So this is upper bounded by let n mean be the minimum over all state action pairs of NSA, right? So then you get this log S squared A over delta divided by n mean. And then you have S times this log S squared A over delta. Oh, there's a factor of 2 and mean. And this is also multiplied with 1 over 1 minus gamma. So if we need to allocate the samples to make this lower bound, make this upper bound the smallest possible, how should we do this? I can control NSA. I have a total budget of so what should be the value of NSA? If I know that for all state action pairs, if I sum up all the samples, I get n. And I want to minimize this upper bound, which is a function of this NSA things. Like, okay, let's call this the n bar and lower bar thing. Right. So Valentin says that so maximize n min, so collect data uniformly. Yeah. So we want this to be the smallest. This whole thing we are dividing by n min, so we want n min to be the largest. So minimizing the upper bound is equivalent to maximizing n min. And the way you can maximize n min under constraints like this is that you just split your samples equally. So NSA is going to be n over SA, in which case this is going to be n min, right? And so then you get this data, which is like 2 over 1 minus gamma squared. And then there is square root SA, some log term, times 2n times 1 plus S over 1 minus gamma. All right. Happy end. This means that if I want this data to be smaller than some value, then the number of samples that I'm going to need is going to roughly scale. So if I want the, oops, no, come on. I want this to be epsilon. Then n is going to need to scale with okay, it's like n s cube so then n is going to be the scale of sh cube over epsilon squared SA. Which is polynomial in all the quantities of interest. So you might call it a day. It's okay. It's not terribly good, especially the h to the power of 6. And also this is like s squared a over epsilon squared, and then h to the power of 6. So here the questions are whether you can remove this. Perhaps it's not really likely that you can get away without seeing every state action pair a bunch of times. Even to estimate the rewards, you would need to have that complexity term. But maybe the s squared is unwarranted. Of course, this is missing log factors, but okay, fine. And then the question is whether the 6 could be improved. Could be perhaps much smaller. So it turns out that as far as the dependence on S is concerned, the dependence on S comes from a reckless way of bounding the difference between the estimated transition kernel and the true kernel. We had to resort to, like we only needed L1 bounds, and then we were bounding uniformly over all next states. That introduces a superfluous S factor. Sort of like you can reduce somehow the dependence on S by being more careful there. So regarding the dependence on age, I suspect you can reduce it. But I was trying to look up lower bounds, and I didn't find lower bounds. So maybe this is one. Maybe it exists. Like I will try to keep looking, but off the top of my hand, I didn't see it. So why? So Vlad is saying, is it S cube? Oh yeah, there is an S squared. S cube, yeah, the S cube should be, yeah, like, that's way too much, right? Yeah, that's definitely too much. Right. Okay, but I will stop here. And the next time we continue by talking about whether anything changes if instead of collecting samples state action by state action, we collect samples along trajectories. And then we start our executions towards using features in large-scale MVPs. Right? That's it for today. Any questions?
So I have a question about learning the model. So in practice, we might not see certain states, so then n would be 0 for state actions. Can we do something there, or can we not say anything?
Again, the story that we saw for planning is going to repeat, right? Like if you can hide a needle in that haystack, then you might need to find a needle in the haystack, and for that you might need to see all state action pairs a bunch of times. So I'm pretty sure that you can prove a worst case bound that scales at least linearly with the number of state action pairs. Like this upper bound here, like we have this S cube A over epsilon squared times h to the power of 6. The lower bound is going to be SA over epsilon squared times h to some power, I don't know what, maybe squared, maybe force. And so that just tells us that effectively you have to see all the state action pairs, no matter what. So there is no hope if you don't have any further hints or structureless MDPs. The story repeats. This is just cruel, right? If you want guarantees, then you have to throw in some additional information, and that's where the features could help, right? Like the hope is that the same way as in planning, we said that you're going to accept these hints in terms of the features. In batch learning, you want to do the same, and you want to ask the same questions.
Right, got it.
And that will hopefully make this condition that every state action pair has to be seen at least once should make go away. But we will see what happens.
Okay. Okay, thanks.
Yeah.
I think there's a couple earlier questions in the chat.
Okay, which were?
The one I was asking was about the probability distribution. If we assume that it's uniform for samples that we didn't get, is it still a distribution over next states? Like, does it still sum to 1?
Yeah.
Right.
Like they're S next states, right? So the sum of 1 over S times is just 1.
But above we define, like, let's say we had just one next state sampled for like state 0 or something. Then with that above definition, we get like a probability of 1 going there, right? And then
oh yeah, so you mean here?
Yeah, like that will sum to 1, and then
that definitely sums to 1, right? Because you can imagine taking a sum over S prime here, right? So that you are asking whether if we take this sum over S prime, this guy.
Oh, never mind. Sorry, I misunderstood what it meant by NSA equals 0. I thought that was for next states, but that's okay. Yeah.
Okay. Yeah. No. Okay. Fine. We just clarified it.
Yeah, that makes sense.
No. It's good. Good. Yeah.
And then I think the question that Wesley had there too, the indexing is that up to NSA? Instead of just N, like the indices for the sum? Or it goes up to N?
N, yeah. Like, yeah. So what you have is that you have this data where T goes from 1 to N, and sometimes STAT hits SA, sometimes it doesn't. So when it hits that particular state action pair, then you take the relevant data. Otherwise, you just ignore it. So this indicator is just like filtering the data. It's just based on whether you're hitting a particular state action pair.
Yeah.
Okay.
Okay, and then I have like a more general question. Like back for even the planning stuff, we like assume that we always have this simulator, right? But how do we get the simulator? like it wasn't like a distribution, right? It wasn't like kind of like this is we're trying to like model the distribution over next states and like the reward model, but then we need like as many as the number of states and actions to keep this model, right? And we kind of assumed for the simulator that we can just randomly sample next states easily. Like how do we actually get a simulator in planning?
I mean, so just to clarify something first, it's probably not answering your question, just like avoid any confusions. If you're estimating a tabular model like this, then of course you can simulate from it, right?
But that's once you've estimated it, right?
Yeah. But okay, so that's clear.
Yeah.
I'm gonna continue.
Yeah.
Right. Okay. So that's clear, right? So this is just one way of estimating models. And then you can think about other ways like featureizing. It's like, I don't know, embedding transition kernels into Hilbert spaces, and like all the crazy ways people think about estimating distributions. As long as, from the planning perspective, as long as the model estimated would support efficient sampling from the transition kernel, that means access by state action pair, and then efficiently being able to sample from the next state distribution, it's okay, right? Like you can have any kind of like density modeling, anything.
Sorry, maybe what I mean is like if we want to solve some problem, we need to get this simulator, right? And in the way we defined it here, we'd need, I guess, a dependence on the state space to get a simulator to then accurately be able to do planning. But doesn't that defeat the purpose?
Well, that defeats the purpose of everything that we said about the features with planning, right?
Yeah.
Yeah, like with planning, we also saw that if you don't have features, you don't have any further help, then it's like your planning time is going to be dependent on the number of state action pairs, which is too bad. So here as well, we see something similar. And now it seems that this is going to defeat the purpose if you are sticking to this tabular modeling. But no, you don't have to stick to this. I'm just saying that, like, in the lack of extra information, if you don't have any further clue or hint about how things are looking like, then this is the only thing that you could do. And the lower bound that I didn't prove, but maybe I will the next time, that will tell you that if you claim to have an algorithm that is able to deal with, batch RL when every state action pair was sampled equally often, and the claim would be that you don't need SA over epsilon squared samples, then I can come up with an MDP where that algorithm would be defeated, right? Like that algorithm wouldn't be able to come up with a good policy, right? So the purpose of batch RL would be to come up with a good policy, and no algorithm without further information can get away with fewer observations than proportional to the number of state action pairs divided by this accuracy parameter epsilon squared. And so it's kind of the same answer to Wesley. And the way to get out of this is to, like you have to make some bet about that, how the world looks like. And if your bet is correct, then you win. If your bet is not correct, you lose. So you can use a, I don't know, GAN or whatever modern technique people use for representing distributions that you can sample from, or variational inference or whatnot, to learn these models. And the first part was that, okay, like if you settle down how you do this, and then you can produce samples from the learned models, how do we use that? And now we need to talk about how we are learning these models, but the first sobering act should be that without, like, there is no free lunch, right? So it's like there is no algorithm that would be universally good for all MDPs unless the sample size is horrendously big for these huge MDPs.
Yeah, so when we talk about planning, would it be like more correct to kind of consider the bound for planning plus getting the simulator?
It's you can do this separately in this order. It's kind of neat that we have this error bound that tells us, where is this? That we can separate somehow the planning, because once you have an MDP, an approximate MDP, you just need to control how good it is. You're only planning for that MDP, and like you're not really concerned about that this is not the true MDP, and you don't pay too much of a price in a way for this. So people talk a lot about how to do better than, so this, what I presented today is called a plugin estimator, or like the plugin approach, or I don't know, separation of estimation and control. But you estimate, you have a nominal model, you plan for the nominal model, you don't care about modeling uncertainty, that you know that your model is not perfect. You don't care about it. You just like plan with it as if like that was perfect. And this error bound tells you that, well, okay, you suffer a little because the model was not correct, but if you can control all of these errors, then it's not that bad. The reasonable question to ask is whether you would be better off if you worried about these uncertainties. As far as I know, no. Like in terms of like simple answers, like worst case optimal results, the nominal planner is doing as well as all the other fancy planners. The way you can win is that if you also want to have a certificate of how well you're doing, and you don't want to get disappointed about this certificate ever, then you're better off by planning in a pessimistic fashion. So then you wouldn't use the nominal model, but you would use a model which gives you like the worst values amongst all the models which are likely given the data that you collected so far. And that has the property that it won't disappoint you if you care about such a thing, right? So if you tell your boss, okay, like my policy, like I optimized it and it's gonna bring in this much revenue, and it doesn't bring in that much revenue, then the boss might be angry. If you use this pessimistic approach, then maybe you're gonna more conservatively estimate the revenue. You're gonna say half of it. Eventually, the two policies are not like the worst case sense. Like there is no distinction between these characters. Like they're equally good. But in one case, you, in addition, has the property that you won't disappoint your boss. So it's like you have this extra guarantee almost for free. And that's a twist that you can play in this setting. And then maybe it's worth the trouble. Pessimistic planning is not a panacea. So it's not really easy to carry through this pessimistic planning in large-scale MDPs. And Alex is asking whether pessimism is just optimism with a minus sign. Exactly. For people who know what optimism is, pessimism is just optimism is a negative sign.
So
It
Vlad,
the exact same computational problems. Go ahead.
yeah, no, I was wondering if Vlad meant like the original question that Vlad was asking, whether it was when we were talking about online planning earlier in the semester, and we computed the sample complexity, how many times we had to access a simulator, but we didn't worry about the cost of constructing the simulator, right? Is that the question you were asking, Vlad?
Yeah, yeah. And do you mean online planning? Or
Yeah,
do you-
like earlier in the semester.
Like, just not to confuse anything. So online planning, in the sense we use it in the course, right? That means that for every state that you encounter, you are doing replanning.
Okay. Yeah, I had that, but I feel like it's similar answer.
Yeah, it is. It's just like separation of concerns.
Mhm.
And I guess there's this, like in the planning problem, we were looking at sample complexity, and we developed various algorithms. And if you want to use one of those algorithms in batch RL, I guess you don't really care about sample complexity because you have unlimited access to the model that you have constructed. So maybe you care more about computational complexity or something. But I guess in all of those algorithms, both of them were similar. So yeah.
Mm.
Right. So the
I was
beauty of the
wondering,
well, sorry, I just wanted to point out the beauty of this result that we use today, that like it applies to online planners too, right? Like you might think that, oh, like you designed this online planner, but like the guarantee was just when it is used in this MDP, which is fake MDP, is not the real MDP. So then like, what the heck, we're gonna use this in the real MDP, then is it going to still work? Yes, like this is the result that tells you that it's still going to work. Okay, go ahead.
oh yeah, I was just wondering if we could get a different type of bound. So, for example, if I give you a batch of data, then try to return me the best policy you could based on that data. Like instead of worrying about things that you might not have seen, because then you can't really expect you to.
But
do
isn't
anything
that what we are doing? Except that the baseline is just V star. So when you're bounding this data, then that just like we're saying that, oh, compared to V star, this is how much we want. Okay, maybe that's like a non-uniform target, but like, I mean, okay, so if you specialize that to a particular state, for example, then like how does it like make a difference that now we are just like saying, oh, maybe we can't get V star, we can only get V star over half, but like that doesn't quite changes the nature of things. You see what I mean? It's like altogether what matters is like how high the value is going to be. We can use any reference value whatsoever. So just by thinking about more models goals doesn't make the job easier or any different. It's actually the same job to maximize the value. Just here the bound was expressed in terms of, you know, like relative to optimal values, but okay. Maybe the bound could made to look like better, to make ourselves feel better if we lower the bar.
So along those lines, what if we use the logging policy as a reference? So what if we asked how much can I improve upon the logging policy? The logging policy happens to be really bad, then you can't do very much.
Yeah.
So yeah, so maybe instead of using V star as a benchmark, right?
Actually, that's a question we're gonna look at Thursday. Like, what's the best logging policy to use?
Yeah. Okay.
Is there a way to improve things by being clever about how data is generated? But okay, so this is like basically in planning, you had access to this MDP, but it was like interactive or active or whatnot. And the difference here is that we kind of trying to do the same thing just with passive data collection. So we can also contrast planning and batch RL by saying that, well, batch RL is just this passive data collection type of thing that we were doing this actively before. And if you think about how big a role this active data collection tends to play, well, it played a lot of different roles. So maybe, well, we should expect that batch RL is going to be more often disappointing than not. It's just you're taking away this option of being clever about how you're collecting the data, and there's only so much you can do without seeing the MDP.
So do you think these results kind of tell us that RL can't really be reduced to a prediction problem? Like they're like control or how one collects data seems to be like something you can't avoid, at least in the worst case.
I mean, it depends on what you mean by can or cannot. If we think that collecting many samples per every state action pair is out of question, then of course the answer is yes. But it was yes already for the active case, unless you are willing to make further assumptions. So, but we will see that it's actually worse. Okay, without, oh, I don't want to give this away. This is going to be fun. So that is still a big difference between this passive learning and active learning. And then it will turn out passive learning. It's just like, can be very, very hopeless. And much, much worse than what it looks from today's bound. Like this bound today is actually a good one when it comes to passively learning. We should be happy with this. If only we can we could get this every time.
So not to spoil it, Shaba, but are you referring to the RL theory seminar from a couple of weeks ago?
I'm not going to bring, yeah, like what I'm gonna talk about is inspired by that. It's gonna be super simplified compared to that, and it's gonna be the same type of separation that Andrea was talking about. And this was like we did a little calculation together with Chen about this. Yeah. It's fun.
But it's the calculations you were doing earlier.
No, actually, I was doing some other calculation at the time. Yeah, that calculation is done.
Interesting result, or?
Like the one that I was occupied with at the moment. I forgot. Of course, it's interesting. All right.